Okay. Today, I present these two topics. Topic one, least squares problem. Second topic, applications of least squares problem. Section 6 is the last section that I teach in this semester. Next week, next Tuesday will be a review section for the final exam. Okay, and next Thursday, low class. Take a review about orthogonal projection onto a subspace, because we need orthogonal projection onto a subspace to solve least squares problem. Take a review. Okay. This is an RN. There is a subspace. Let me call the subspace W. Then W is a subspace. A span by some vectors, say U1, U2, and UP. When P is 2, then W, the graph, is a plane, right? A set spanned by 2 vectors is a plane, right? But P can be greater than 2. Then W be a subspace of Rn. That means that each vector is an n-dimensional vector. Okay. Also, I assume these vectors are linearly independent. You cannot draw any of them, okay, from the spanning list. With the basis means a smallest spanning set. A smallest spanning set. With the basis U1, U2, UP. Yeah, we cannot drop any of them and still span the same subspace. Yeah, here is the graph of W. And then Y, a point in Rn. Yeah, say Y is here. This is Y. Suppose Rn, the origin is here, 0. Yeah. Then the orthogonal W, the subspace has infinitely many points in W. Now the question is, which point in W that has the shortest distance from to the given point 1? Which point has the smallest distance to the point 1? It turns out that to find the point, orthogonally project the given point onto W. The projection point is the point that has the smallest distance. The orthogonal projection, the notation is projection of the point Y onto W. Okay. The orthogonal projection is how to find the orthogonal projection. Project this. Okay. Yeah, here. This point, the rotation is this, but I use a y hat. Y hat. Okay. Y hat, of course, is projection of the point Y. Yeah. Now, the question is how to find Y hat. The formula is the following. Okay. Y hat, the projection of Y to W. Because Y hat is in the subspace. Subspace, all the points in the subspace W is a linear combination of the basis vectors. So this guy should be a linear combination of the basis vectors. So let me write alpha 1, U1, U1, linear combination. Alpha P, UP. Then how to determine the coefficients alpha 1, alpha 2, and alpha P? Okay. Where alpha 1, alpha 2, alpha P is the solution of the following linear system. A transpose times A. The unknown vector is alpha. Solve this equation to get alpha, then to get the coefficients. Then compute this linear combination, then we have the orthogonal projection of Y onto this subspace W. Okay. Then what is A? Okay, here A. What is A? Where A is the matrix obtained by combine the basis vectors. First column is U1, second column U2, and UP. Yeah. This is A. Okay. This is A. Alpha. What is alpha? Of course, alpha, this vector is alpha 1, alpha 2, and alpha P. Alpha P. So this point is the point in the subspace W that has the shortest distance from the given point. Okay, yeah. This is a review about orthogonal projection. Now, I use orthogonal projection to solve least squares problem. First, let me explain what is a least squares problem. Topic 1. Topic 1 today. Below that, log every linear system AX is equal to B. Here, A, the size is, say, for example, n by n. X, a matrix times a vector make this computable and should be n by 1. Okay, n by 1, a vector that has n entries. Then what is the size of B? Look at the left-hand side. N m by 1 times n by 1. No, m by n times n by 1. The result should be m by 1. Therefore, B should be m by 1. Not every linear system has a solution, right? We know this, right? An example, easy to generate. One example, say for example, take a look. For example, consider this linear system. The unknown x1, x2, right side to 0, 11. This linear system, if you write it in equations, the linear system has 3 equations and 2 unknowns. This linear system has no solution. Why? Solve it. Augmented matrix. Augmented matrix. Right? 4, 0, 0, 2, 1, 1. Right side. Perform elimination to reduce the augmented matrix to an epsilon form. We get 4, 0, 0, 2. At 10.5. Yeah, 10.5. This is a 1 epsilon form of the augmented matrix. Each row actually is an equation. Look at the bottom non-zero row. The bottom non-zero row says that x0 times x1, 0 times x2 is equal to 10.5. No matter what values you assign to x1, x2, we cannot make this equation true. So this linear system has no solution. Okay, this is a inconsistent linear system. Hey, now, inconsistent. Let me write this down. Inconsistent linear system. Linear systems arise frequently in applications. In applications, more inconsistent linear systems than consistent linear systems. Okay. Most of the problems, they don't have solution. Okay. When a solution is demanding for an run x6 because the linear system has no solution, so run x6. Then what we can do? The best we can do is to find an x. Yeah, linear system. Yeah, here. Linear system. This linear system may have no solution. Then when the linear system has no solution, what we can do? We still want to get something about this linear system. What we can do? Okay, X, the unknown is actually the unknown is in Rn. Okay, in Rn. Yeah. Phi and X in Rn. That make Ax is equal to B. That makes the left-hand side and the right-hand side as close as possible. Okay, makes Ax left side as close as possible to the right-hand side. The best we can do. The linear system has no solution, but we still want to get something. So we want to find some X so that left side and right side, their distance as small as possible. Left side, right side, distance, left side, right side, distance. We have a formula for distance, a vector and a second vector, distance. The formula is the vector minus second vector, then take log, take length. This is the distance, right? All right. This problem actually is phi and X, so that left side is as close as the right side. This problem, we call it, give a name, least squares problem. Okay. This problem, phi and X, that make left side as close as possible to the right side. We name this problem least squares problem. Why we use least squares? Because the distance, actually by formula, we call it is square root first entry minus second entry square plus a first entry of this vector minus the first entry of this vector plus square, okay? Second entry of this vector minus the second entry of this vector, then take square, yeah, and so on. So here, it is under the square root, it is the sum of squares. Now we want to minimize the squares, so least squares, yeah, squares here, squares, least squares problem. All right, here is the precise definition of a least squares problem. Okay, yeah, here definition. Okay, the following we name least squares problem. Okay. Yeah, definition means the meaning. Okay, precise meaning. Okay, definition. Suppose consider this linear system. We assume matrix A very general, m by n, x m by 1. The right side m by 1. The right side m by 1, because the left side m by n times n by 1 is m by 1. Okay, so right side m by 1. Consider the solution of this linear system. I don't know, maybe this linear system has no solution. Okay. Now, definition. At least squares solution of this this linear system is an x. Let me call this x hat, special x in Rn, right? X is in Rn. So a least squares solution of the linear system is some x in Rn, such that this x make left-hand side and the right side as close as possible. Okay, such that A times this special x hat minus B right side length. This is the distance between left-hand side and right side. This distance should be the smallest distance. That means that less than or equal to A times any x in Rn minus B. Yeah. Any x in Rn. Left side and right side, the distance should be greater than or equal to the distance. This distance. Okay. This is true for all x in Rn. If you can find such x hat, such vector x hat, then we call x hat is a least squares solution of the linear system. Not the exact solution of the linear system, but least squares solution. Yeah, make squares, you see here, squares. Make this the least. Okay. This is a precise meaning of least squares problem. Okay, now how to find x hat? We need to use orthogonal projection. Okay. How to find x hat? Okay. First, let me cut the matrix A into columns. How many columns? Where? Here, I assume A is m by n. A has n columns. First column, A1, A2, n columns. N columns. And let A be divided into columns. And let W be the space spanned by the columns. That means that W is column space of A. Yeah. Okay. What it means, column space, by definition. W is spanned by the columns. Because each column, how many entries has, I assume matrix A, m by n. So each column has m entries. So each column is in Rn, right? Rn, right? Each column is in Rn. So each vector is in Rm. So W actually is a subspace. Yeah, this is a subset. Okay, subset rotation. It is a subspace of Rm. Okay. Further, W is the set spanned by the columns. What it means? Span, linear combination. That means that x1 times A1, x2 times A2, xn times an. Yeah. each element of W is a linear combination of the columns. Okay, where x1, x2 scalars, arbitrary scalars, numbers, arbitrary numbers, right? So W column space, it is the set of all possible linear combinations of the columns. And I can further write linear combination as, further write this. Okay, what is this? Linear combination of vectors. Okay, the vectors are columns of the matrix A. So I can further write this actually. A matrix A, matrix A times vector X. Where vector X, of course, is in Rn. Okay, Rn. Okay, arbitrary. So W is the set of A times X for arbitrary X. Let A be this and W be column space of A. Now let me plot the graph of W. Say W is in Rm. So Rm, the graph of W is, say, I use a plane to represent W. Okay. W. This is W. Okay, W. Rn, the origin is here. Origin is here. Right. Now, B, this vector is M by 1 vector. B is in Rn. This guy is in Rn. Okay, B, say here. This is B here, B here, B here. Now the question is, now the least square. Okay, now the least squares solution x hat is make A x hat minus B. That means that A times x hat is a point in W. W is the set of A times X, any X. So A times X hat, this is a point in W. Minus B, the length. So this is the distance between this point and B. Least square, go back to the definition. A times X hat minus B, not greater than A times X. Again, this is a point in W, minus B. Actually, this is okay. A times X is a point. Let me denote the point. W hat minus B. This is okay. This is for all X in Rn. Rn. So let me denote this point W. B. For all W in W. In W. A times X is a point in W. Okay. Now, least squares problem actually is find a point on W. The point has the smallest distance to the point B. Okay, yeah. W hat minus B distance is less than or equal to W any point in W in the space W minus B distance. Yeah, actually, this solution is in the review here. Yeah, solution. Yeah, orthogonal projection. W is a subspace. Which point in W has the smallest distance to the given point? Projection. Okay, projection. Right. So yeah, W hat the solution. The solution lies in orthogonal projection. Yeah. Project this point orthogonally onto W. Yeah. This is a B hat. B hat. Yeah. This point should be A times X hat. A times X hat. Yeah. So this point, okay. So then how to find the projection? Okay, how to find the projection? Okay, by formula, the projection is a linear combination of, because our projection is a point in the space, so this is a linear combination. Yeah. Let me X hat. Okay, because I had okay here A1 X2. No, this is a number, not a vector. A2 and so on. How many vectors? AN. What is X hat? X1 hat, X2 hat, Xn hat. Where? X1, X2, the coefficients, is the solution of the linear system. Which linear system? A transpose times A. Then X is A transpose times B, the vector B. Yeah. Solve this linear system for X. Then to get the projection point. The projection point should be W hat. Yeah, this is a W hat. W hat. W hat has the smallest distance to B. Yeah. Yeah. Actually, this guy is a B project onto the subspace W. Yeah. Okay. Now, let me summarize this discussion into a theorem. Okay, a theorem. Okay. Yeah. Theorem. The solution of this equation the solution of this equation, yeah, this equation, the solution is this. Okay, the solution is this. This guy make A times X hat be the projection of B onto the subspace W. So the projection, the distance from B should be the smallest. Yeah. So The solution of this equation actually is the least squares solution of the original linear system. How to find x so that left side and right side they have smallest distance. Solve this equation for x. That x is the answer. Yeah, this is a figure. Now, let me show you examples about how to use the freedom to solve problems. Okay, so example one. Example one. Example one. Use the example. This is should be example two. Yeah, example one here. Let me use this linear system. Okay, this linear system has no solution. Now let me try to find x1, x2 so that left side and right side they are as close as possible. This is example number two. Okay. Still consider the same linear system in example one. We know that this linear system has no solution. No solution, right? No solution. Okay, now how to find x so that left side, right side they have smallest distance. Okay. According to the figure, solve this equation. Yeah. The answer is solve A transpose times A x is equal to A transpose times B. Matrix A. Matrix A. Now take transpose. Take transpose, we get 4, 0, 1. Column becomes a row. Second column becomes the second row. This is an A transpose. Times A. 4, 0, 1, 0, 2, 1. And x. X, of course, let me write x, okay, in detail. Two unknowns, x1, x2. And then A transpose times B, B is here. It is 4, 0, 1, 0, 2, 1, A transpose. Times B. Okay. Compare left hand side, this matrix times this matrix. It is 17, 1, 1, 5. Right? This matrix 2 by 3, and this is 3 by 2. So the result 2 by 2. Yeah. Yeah. Unknown. This matrix times this vector 19, 11. Solve this linear system for the solution. Okay. So the solution is 1, 2. 1, 2. This vector make left side, right side as close as possible. Okay. Have a check. Okay, check. Have a check. Arbitrarily pick a point. Arbitrarily. Okay, this is x according to the definition of least squares problem. The least squares solution is denoted by x hat. So here, x hat. Okay. Now I want to have a check. X hat make left side, right side as close as possible. Arbitrarily pick x. Say pick. Say for example, -1, 2. Yeah. Then compare. Okay. B. Yeah. B. Right side. Yeah. B is this. Okay. B minus A times x hat. The length of this vector. This is the distance between left side and right side. Compare it. Okay. Now A, which is A, times x hat, this vector. Then subtract it from B. Then take length. The number is square root of 84. Actually, this is the smallest possible distance between left side and right side. Right. Now, let me compute the distance corresponding to x, -1 and 2. B minus A times x. Now this time, not x hat. So A times x. That is left side. Left side minus B. Take length, distance. You get square root of 152. Yeah. Greater than this. Actually, greater than, not equal. Okay. Yeah. This number larger than this number. So this shows that, yeah, this is makes sense. It is a least squares problem. This x make left side and the right side the distance, the smallest. Yeah. Okay. This is one example. Yeah. Example 1 says that this linear system has low exact solution. But we still want to get something. Then we turn to least squares solution. Least square solution is this. Topic 1. Second topic. Applications of least squares problem. Let me show you 2 examples. In practice, okay, 2 examples. There's topic 2. Applications of least squares problem. Topic number 2. Yeah. Example 1 under this topic. A ball is flow. Okay. A ball is flow. And times t means time. Okay. At times 0 second, 1 second, after 1 second, after 2 seconds, 3, 4, 5, and 6. Okay. The height of the ball are measured as, okay, the height. Let me use an h to mean height. When time is 0, the height is 0. Originally, the ball is on the ground. When time is 1, say 1 meter. When time is 2, 3 meter. 8, 7, 4, 1. Okay, yeah. Let me draw a graph here. This is a graph. Okay, graph. Suppose someone is here, so I call this origin. Okay, origin. Yeah. When time is 0, the ball here. When time is 1, the ball is 1 meter. When time is 2, 3 meter. When time is then 8 meter, then 7, right? 7, then 4, then 1. 1 meter. Yeah, 1 meter here. Now the question is find a parabola. Find a parabola C D T time. Okay. CDE. Okay. Find a parabola. That means that determine CDE. Find a parabola that comes closest to the H values. Yeah, to these H values. Okay. Let me draw the parabola. Yeah. Draw parabola. There are infinitely many parabolas. Which parabola best fit these data points? Which parabola best fit these data points? Yeah. Okay. Now the solution is okay. Solution. Yeah. Okay. Okay. Then the values of the parabola, this parabola, let the values of the parabola form let the values of the parabola at time 0, 1, 2, 3, 4, 5, 6 form the vector. Okay. Yeah. The value of the parabola at 0 is this: y of 0, y1, and so on. Y. The last time is y6. Yeah. Form a vector. Okay. Let me denote this vector by a letter, say P. P means parabola. Okay. Yeah. The value of this function at these times, I put them into a vector. Okay. In detail, y of 0. What is y of 0? Plug in 0 in T. So it is C times D times 0. Yeah. What is y of 1? Plug in 1 in T. 1 squared. Similarly, y at 2. T is 2. Yeah. 2. And so on. Y of 6 is a C plus D 6. E 6 squared. I can write this vector as a matrix times a vector. Okay. It is 1, 0, 0. Times this vector C D E. Yeah. You see? 1, 0, 0 times C D E. Yeah, actually it's this. How about the second entry? 1, 1, 1 square. 1, 1, 1 square times this vector is this. How about this? 1, 2, 2 square times CDE is this, and so on. So the next row is a 1, 3, 3 square. And the next row, 1, 4, 4 square. So the last row, 1, 6, 6 square. Okay. Yeah. Actually, yeah, this P. Yeah. Okay. Now what I want to do, I want to choose CDE so that the values of the parabola is as close as possible to the given value, to these values. Okay. Okay, now let H be the vector formed by the given values. Yeah, given value. Yeah. 0, 1, 3, x, 7. Yeah. Let me put them together into vector. 0, 1, 3, 8, 7, 4, 1. Okay. What I want to do is we want to minimize. We want to minimize P. Yeah, P here. P. The vector of values of this parabola at the time 0, 1, 2, and so on. We want to minimize P, the distance. P distance from H. So minus H. Then take length. This is the distance between P and H. H is a vector of the given data. Okay, given data. Okay, now this is a least squares problem. Why? What is P? P actually this matrix times this. Okay, let me plug in this in P. This is a 1, 0, 0, 1, 1, 1 square, 1, 2, 2 square, 1, 3, 3 square, and so on. The last row, 1, 6, 6 square times CDE. What is CDE? We need to determine that. Okay, this is a P minus what is H? Yeah, this is H. C F. And then length. How to choose CDE so that A times this minus this vector. The distance means left side of the linear system. Okay, yeah, the linear system. Let me denote this by A. This is of course H. Yeah, minimize this. Minimize this vector minus this vector. That means that phi x. Yeah, this is x. Phi x, so that left hand side and the right side as close as possible. It is a least squares problem. All right. By theorem, how to find least squares problem? Yeah, theorem says that solve this linear system, then the solution is the least square solution. Okay. Yeah. Okay. By theorem, solve A transpose times A, x. A transpose times the right side. Yeah, right side. Then what is A? Yeah, this is A. What is X? This is X. What is the right side? This is the right side. Okay. 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 Now the solution is I can move this vector, move this matrix to the right side. The solution is this. A transpose times A, then inverse times A. Move this way. Assume this matrix is invertible. Move it to the right hand side. Then this is the solution. The solution is A transpose times A. Compute it. Then compute inverse. Then multiply the inverse to A transpose times H. Then the answer is this. 2 points. Of course, not by hand, by calculator or by computer. The solution is this. This is a C. This number D, E. So there are many parabolas. Which one best fit the data? Best fit, that means that it has the smallest distance to the data. That one is, the solution is the following parabola. C, 2.317. D, T, okay, and then T square. This is the solution. This is the best parabola that fit the data. That fit the data. This parabola has smallest distance to the data. This is one example. Now, second example. Example 2. It is about whether the table below lists the temperatures from day 1 to day 5. The table here. Day temperature. In the first day, say the temperature on average 52 degrees. 2, 55 degrees. Day 3, 58 degrees. 4, 53 degrees. 5, 49 degrees. Okay, now the question is 5 and 9. Let me plot this data. Plot the data, plot the data. X-axis is day. Y-axis temperature. Okay. Day 1 temperature 52. Say here. Day 2 55. Day 3 58. Then day 4 53. Day 5 49. Okay. Now 5 and 9. And 9, the equation is C plus D. T time, right? Day. T the units. Days. Okay. Days. Time. Then best fit the data. There are infinite many lines. Which line is as close as possible to the data? Yeah, which line? Which line? Okay. Okay. All right. Yeah. To answer this question, okay. To answer this question, find the line that best fit the data. We minimize. Minimize. Okay. Okay. Y at 1 minus the data 52. This is the distance of the line to this data point. Okay. To avoid cancellation, so I make this positive. Say take square. Then pass the distance of 1 and 2 to the second data point 55. Yeah, this is the distance of y2 to 55. This number can be positive, can be negative. I don't want this number cancel this number, so take square, make it positive. Take square. Yeah, then sum. Similarly, y3 minus 58. Yeah, 58. Take square, and then yeah, y4 53 square, and then y5 minus. This is a sum of squares of distance of a line to the given data points. Yeah, I want to minimize this sum, the total distance. I want to minimize. Let me write this into vectors. Okay, into vectors. Actually, this is y1, y2, y3, y4, y5, this vector, minus the vector of the data, 52, 55, 58, 53, 49. Yeah. A vector minus a vector is y1 minus 52. Yeah, y1, 52. y2 minus 55 here. Yeah. And then this is a vector. Take length on this vector. Length, square root of first entry square, second entry square, and so on. But here, this sum has no square. So take length, then take square to cancel the square root. Okay, so yeah, actually, the sum is this vector minus this vector. Take length, then square. Okay, now let me write this vector into a matrix A times unknown C and D. Okay, yeah. It is y1 is y1 is C plus D times 1. A line y is C times D times X. Okay. Y2, Y3, Y4, Y5. Yeah, vector. Minus the data. Yeah. And then the length square. Okay. Okay. Now this guy, I write it into a matrix. Which matrix? 1, 1, 1, 2, 1, 3, 1, 4, 1, 5. This matrix. times the unknown CD. Yeah. Make this message times CD is this. Then minus. Yeah, length, then square. Okay. Now, how to choose C and D? Make this quantity as small as possible. This is a least squares problem. The solution is, according to the theorem, the solution is, let me call this matrix A. This is a X, and this is a B, say, B, right, for example. Yeah. How to choose X so that A times X minus B as small as possible? By theorem. By theorem. Okay. Solve this equation. Solve this equation. Okay. Then the solution is, what is the solution? Let me see. I skipped the detail. Oh, the solution is 55.8, negative 0.8. Yeah. Actually, this is a C, D. There are infinitely many lines. Which one best fit the data? Yeah, the solution. Okay. The line. Okay. That is closest to the given data is this line. C, this C. D. T. Okay. T means day. Okay. The units of T is days. Okay. Times T. Yeah. Times T. This is the best fit the data. Okay. Okay. Now, one more question. Okay. One more question. After we get the line, one more question. Okay. After we have the line, predict the temperature in day 6. Okay. In the table, we have data from day 1 to day 5. Now, can you predict the temperature in day 6? We can use this model. Okay. We can use this model. Plug in 6 in T. Times 6. Okay. It is 51. Okay. So based on the given data, we can predict that day 6, the temperature on average about 51 degrees. Yeah. This is example 2. Yeah. So I finished with this section 6.6. I finished the teaching in this semester. Okay. So next Tuesday will be a review section for the final exam. Okay, for a final exam. And next Thursday we don't have class.